Yeah.
So in the first example, if A occurs multiple times in the regular expression.
Give me an example.
Like if it is A followed by A or B.
Okay.
And we, when the,
So then this A is going to match the first. So if you say, then this A is going to match this, and so what you're going to be left with is
but
that.
it could also be seen A from the second part.
How can it be? How can you be, right? How can you have a match for something like this if you're going to skip? You're not allowed to skip, right?
But didn't we skip in the last but one example?
That's why I said that is a star, right? So it can be, that can match, that can become the empty string, right? The A or B star could be just empty. Okay, so that is why you are skipping past. Okay, otherwise you can't skip past. Okay, so we are, that's a good question because that's exactly what we are trying to define here. Okay, so we define something called includes epsilon, which is a function on regular expression, and basically says, okay, does this regular expression, match the empty string? Okay, so includes epsilon of A is false, right? So any alphabet, well, it's going to match only that alphabet character. It's not going to match the empty string, so it's false. If you have R1 or R2, then if either R1 or R2 can match the empty string, then includes epsilon of R1 or R2 is true. Okay, so that's why we say includes epsilon of R1 or R2 is equal to includes epsilon of R1 or includes epsilon of R2. Okay, if you have concatenation, well, only if both of them can match epsilon, only then the R1 R2 can match epsilon, right? So if either one is non-empty, then obviously the concatenation is not going to, the concatenation is going to be non-empty, right? And as a result, you have an and includes epsilon of anything, closure of anything is always true because we define closure as epsilon or multiple repetitions, one or more repetitions of that thing, right? So includes epsilon of R star is always true. Okay? And you can very easily see that this is a linear time computation, right? So you have a regular expression, you can compute this in linear time. Okay, so now let's define, now that we have this auxiliary definition called includes epsilon, then we can define what is a derivative. Okay? And if you want to match, if your regular expression is A and the symbol that you see is A, that means you've finished the match. Okay? And so when the derivative is epsilon, that means you have finished the match. There's nothing more you need to see. Okay? So when we use the derivative to construct an automaton, then whenever the derivative is epsilon, then we would mark the corresponding state as an accepting state. Okay? But if the regular expression trying to match is B, and it has to, as a character you're seeing is A, then what do? Well, then you have no match, and that's what you indicate by saying it's empty. It's 5, right? So the match cannot be continued. There's a failure, right? 5 says match failure, right? Whereas epsilon says match complete, and you are at an accepting state, right? So whereas phi corresponds to a failed state, so you are declaring that there is no way to match this string. Okay? So R1 or R2, then again it's intuitive. So you are going to either this A might match the first character from R1, or it might match the first character from R2, and therefore we simply push this derivative operation down, okay, to R1 and R2. And if you have R star, then what we are trying to do is we are trying to say, okay, there are, if you see an A and you need to match R star, okay, so clearly in that case R star cannot become epsilon, right? Because if it did, then epsilon is not going to be it's not going to equal A, right? So certainly that's not a possibility. So the only possibility for matching R star when you see an A is that R star produces at least one copy of itself, right? So then you can write R star simply as R followed by R star, right? And once we do this, we already have this rule for dealing with concatenation, which basically says, okay, I'm going to match A with A of R1. Okay? So the simple case is that I'm going to match A with only something from R1, and R2 is left unaffected. Okay? That is true if R1 can never be empty, right? But if R1 can be empty, then in a match for R1, R2, you might end up, R1 might end up generating empty, and A might match the first character of R2, right? So that's why we have the alternator. So this is the condition. We check if R1 can includes epsilon. If it doesn't include epsilon, then you know that, okay, it's not empty, therefore A must match something from R1, and that's what we're saying here. Okay? But if it can be empty, then A can match either something from R1, or R1 may become empty, and A can match something from R2, and that's what we're saying here. So it matches, in this case, A is matching something from R1, right? And then, of course, entire R2 is left at this point in order to match. And whereas here, you have counted the possibility that A doesn't match anything in R1, R1 becomes empty. Now A is simply going to match R2. Okay? And closure is simply an application of this concatenation rule for the case where R star expands to R star, right? Remember that R star is actually defined to be epsilon or R followed by R star, right? This is the definition of closure. So we know that if you want to match a symbol A, that cannot match epsilon. So that's why we basically rule this out. We consider only R star, and then we simply apply this rule, and that's how we get to that rule. Okay? So the point here is that, once again, I want to emphasize before we stop, is that the language accepted corresponding to the epsilon is the set consisting of a single string, whereas the language corresponding to the empty set is the empty set and it doesn't match anything. Okay? So let's stop here and we'll continue next lecture, where we will talk about how to take these derivatives and use them to construct a finite state machine.